So, we will discuss drafting force in today's lecture. Drafting is all about withdrawing fibers from the drafting zone. As we have already understood the drafting part, that within the drafting zone there will be always two group of fibers, one group of fibers moving at front roller speed, another group of fibers moving at back roller speed, and what is happening is that we are continuously withdrawing the fibers, we are shuffling the fibers within the drafting zone, and as a result of this shuffling actions or sliding action between the fibers, there will be a lot of force which will develop on the fibers, which we call drafting force. Let us first concentrate on the force development on a single fiber as this fiber is withdrawn. So, let us look at this diagram. One drafting zone has been depicted here, and there is one fiber shown by the orange line, and the fiber is being withdrawn. It is under the nip of front roller, therefore, it is moving at a higher velocity now and going to be separated from its neighbors. As it is being moved away from the drafting zone at a higher speed, the fiber is going to experience frictional resistance to its movement. From whom? From the slow moving fibers, because this fiber is in contact with many fibers. Many of those fibers are moving at a lesser speed than this fiber. Therefore, there is going to be some amount of frictional resistance to its movement. Slow moving fibers are going to resist its movement. If we assume that the frictional resistance per unit length is constant, which actually may not be true, but let us assume this, the cumulative frictional resistance will increase from end B to end A. So, we have a fiber here, the forward end is A and the back end is B. So, the frictional resistance will increase from tip to the tail part of the fiber, all right. So, as a result of this, what is going to happen? The fiber will not be at constant tension, but the tension on the fiber will change along its length. The tail on end of the fiber will have minimum tension, and as we move towards the tip, tension is going to increase, because more and more fibers are trying to oppose it. So, there will be cumulative resistance to its movement. This is the cumulative frictional resistance to its movement, and therefore, as a result of friction, the fiber is going to be under tension. So, at the tail end, the tension is going to be 0, but along the length of the fiber, as we move towards the tip, the tension of the fiber is going to be more and more. That means, on a single fiber, the tension is not constant along its length, the tension is going to vary from one end to the other end, and this is going to happen with all the fibers which are being withdrawn. Now, if we try to understand what are the various parameters which are going to affect this tension development, because what is going to happen in one fiber, it is going to happen on many other fibers. So, according to Cox, transverse force per unit length Q acting on a fiber in a sliver subjected to a lateral pressure P is given by the equation as shown here. That is, this is small q is equal to 2 df into p by 1 minus eta. So, what is df? df is the diameter of the fiber, p is the lateral force which is acting on the fiber from its neighboring fibers, and epsilon is the porosity of the fibers, that is ratio of volume of air to the volume of fiber. So, this particular derivation was done by the scientist Cox, and this gives us an idea that the transverse force Q on a fiber which is within a sliver, and let us say we are trying to pull out the fiber from a sliver, then this is the force per unit length the fiber is going to experience, which is a function of diameter of the fiber, the lateral pressure which is acting on the fiber, and the porosity of this fiber, that is compactness. In a way, this is compactness of the fiber. If the fiber is porous, it is less compact. If it is not so porous, that basically means it is more and more compact. Since diameter of the fiber varies, diameter may not be constant. Therefore, this equation was slightly modified, and we get the another equation as shown below, that is small q is equal to 2 dAp 1 minus epsilon, and within third bracket we have 1 plus 5 by 4 C d square, where C d is the coefficient of variation of fiber diameter. So, that is a little modification of the equation which was done, and from there we go to the next slide. So, if we know the force per unit length, lateral force that is going to act on the fiber per unit length, now we can then write force required to withdraw a fiber from a sliver is going to be F is equal to mu q L. So, what is mu? Mu is the coefficient of friction between the fibers. Small q, as told, is the lateral pressure which is acting on it, that it is the normal force, and L is the length of the fiber. Therefore, force of withdrawal is going to be mu q L. Now, there is very interesting fact, since even when P is 0, that if we do not apply any pressure on a sliver in lateral pressure or transverse pressure, some force is still required to remove a fiber from sliver. This you can also experience, that even if we try to remove a fiber from a sliver, the sliver is not under any pressure, still we need little force to withdraw or to remove the fiber. Why do you need this force? We will come to it later. If that force is k, let us say, then the force of withdrawal is going to be mu q L plus k, where k is the minimum force that I need to remove a fiber when there is no external pressure acting on the sliver, and therefore, this equation, full equation, we should add the value of k and we get this equation. Now, we have to understand what is the origin of this k, why that we find little force is required to withdraw a fiber even when there is no transverse pressure on it. K is due to the presence of lubricating oil, locked in strain in fibers within the sliver, mechanical interlocking between the fiber ends due to crimp and due to hooked ends. Because of all this, a little force is required to remove a fiber even when the sliver is not under any pressure, any external pressure. And from here we can say, if I look at the equation, we can always say that long and large fibers, large diameter fiber will require more force for withdrawal from a group of fibers. If I want to withdraw a long fiber, I need more force. If I want to withdraw a fiber which is larger in diameter, I also need more force. and if the pressure on it is more, then also we need more force, because P appears on the numerator, and if the coefficient of friction is high, see it may vary from fiber to fiber, the mu value depends on the type of lubricating oil we apply on the fiber, or spin finish oil in the case of synthetic fibers, or in the case of natural fiber it is the natural wax which is there. So, it all depends on these factors, that is mu depends on the nature of the surface of the fibers, and it also may depend upon the moisture which is not there in this equation, but mu value depends on that itself is another lecture, that the friction between fibers, what are the various factors which affect friction, but there are many parameters which affect fiber to fiber friction. The other thing is epsilon, that is the porosity. So, as I told already that if the sliver is very compact, that means its porosity is less, epsilon value will be low. If the sliver is very open, then its epsilon value is going to be very high. So, the porosity also matters, because porosity will decide the degree of contact between the fiber. That is why it comes into the picture. If a fiber is not so porous, if it is very compact, let us say we have passed it through a very a narrow trumpet and made it very compact, in that case this fiber strength is going to increase, because the fibers will come very close to each other, and hence they will establish lot of contacts between them. So, this is how the force that we need to draw a fiber depends upon many factors. From here we go to the now drafting force. So, whatever we have discussed is all about withdrawing a single fiber from the drafting zone or from a sliver. Now, in a drafting zone, as was told, that there is not that there is only a single fiber is being withdrawn, there is a large group of fibers which are arriving in the drafting zone, and similarly a large group of fibers are being removed from the drafting zone. So, fibers are continuously entering the drafting zone, and they are continuously being removed from the drafting zone. So, fibers within the zone can be classified into two groups already mentioned, slow moving fibers and faster moving fibers, and there will be always a group which is intermediate fibers moving at intermediate speeds, that is those are basically floating fibers. We also discussed about floating fibers, any fibers whose length is less than the nib to nib distance, they behave like floating fibers. So, anyway, broadly we can classify them into two groups, slow moving fibers and fast moving fibers. The faster moving fibers experience frictional resistance to their movement from slow moving fibers. Obviously, slow moving fibers will try to resist them, they are moving at a lesser speed. The faster moving fibers which are in contact with them are trying to move at a faster speed, and hence there is going to be a resistance, because they are in contact with each other. So, drafting force is therefore is the frictional resistance to slippage between these two group of fibers. The resistance that is offered by the slow moving fibers on the faster moving fibers, this resistance is manifested as force, and we call it drafting force. Whatever force develops within a drafting zone, this force will act in both the group of fibers, that is they will act on the slow moving fibers, they are also going to act on the faster moving fibers. So, the magnitude of the force is constant on both the group of fibers. Fibers moving out of the front roller speed, that is these fibers which are being withdrawn, they are actually less in number than the fibers which are moving at back roller speed. That means, slow moving fibers are more in number than faster moving fibers. Therefore, the average force per fiber held by the front rollers is more than those held by the back rollers. Force is same, number of fibers gripped by the front roller is less in number, and they will be less by how many times? It will depend upon the draft. If the draft is 6, their number will be 6 times less in comparison to the numbers which are gripped by the back pair of rollers. If it is so, therefore, what will happen? The magnitude of force per fiber moving out of the drafting zone will be more, whereas the force acting per fiber moving into the drafting zone, that the fibers which are gripped by the back roller will be always less. Now, we go to this topic, that is draft versus drafting force. How the drafting force is going to be affected by the draft that we keep in the drafting zone. Now, if we look at the diagram shows a plot between drafting force per fiber versus draft, and we get a plot where we see that initially there is a rise, the force increases, it reaches a peak. After reaching a peak, as you increase the draft, the force declines, and it continues to decline with the increase in draft. So, what happens to the drafting force as we increase draft? Drafting force may increase, drafting force also may decrease. It all depends in which zone we are working. In the initial part, with increase in drafting force is going to increase, whereas I can divide this trace into two parts. If I draw a line vertically from the peak downwards, the left hand side means that with increase in drafting force increases, and from the peak if I go to the right hand side, then we will conclude with the increase in drafting force reduces. Therefore, if the question is raised, what happens to the drafting force when draft is increased, the answer could be force may increase and force may decrease. Both are true. It all depends what is the level of draft, what is the magnitude of draft. If the draft is less, that is than where we get the peak, then in that zone force is going to increase with draft, otherwise force is going to decrease with draft. So, we can, in the picture, we can divide the trace into three regions: region 1, region 2 and region 3. The region 1 is characterized by increasing drafting force with draft. So, here the force increases with draft, and why does it increase with draft? The reason is that as I slightly stretch this fiber, what is going to happen, that the crimpy fibers are going to lose their crimp, and there will be a contraction of this fiber. This fiber is going to contract laterally, and because of the lateral contraction, what is going to happen, the fibers are going to come closer to each other. So, as they come closer to each other, the stiffness increases, that you need more force to stretch the fibers, and therefore, what happens is this, the force keeps on rising in this zone. So, in this zone force rises, but there is no sliding action going to happen, that is, there is not going to be any shear between the fibers in region 1. Because of the uncrimping or decrimping of the fibers or orientation of the fibers, since many fibers may be disoriented state, they are getting straightened out, there will be overall increase in stiffness, and hence the force is going to rise and rise and rise. So, that is the reason why you get a rise in force initially. Region 2 is characterized by stick slip phenomena. It is the critical region. The sliver contraction stabilizes and the slippage between fibers have just started. So, here is a zone, is a very unstable zone. We call it very unstable zone, the region 2, where fibers are going to slip and then they stop slippage also. So, there is a fluctuation in the force stress. This is a very unstable region. In this region, if we maintain the draft, the fibers will move in a stick slip manner within the drafting zone, and that will be the source of irregularity into the drafted product. So, here is a zone where force will increase. The moment the fiber starts slipping, the force immediately falls, and when the force falls, again the fiber gets stretched, again the force rises, and again the moment it starts slipping, it falls. So, it moves up and down, and that is how the trace we get. Once we cross the peak, now with the increase in draft, the force is declining. So, it is characterized by a steady slippage of fibers as the primary mode of sliver deformation, that is the region 3. That is, we overcome the stick slip zone and then we reach a zone where we get steady slippage between the fibers. And as the fiber slips, as we get more and more draft, what is going to happen? The number of fibers under the front roller is going to decline. So, their number going to be decreased, and we will see later when the numbers are going to decrease, then drafting force is going to be less, because the contact, the total area of contact between the two group of fibers will be less and less as we increase draft. Therefore, friction and resistance will be less and less as we go for higher and higher draft. The more draft we give, lesser and lesser will be the number of fibers under front roller, and therefore, the total contact area between the two group of fibers will be less and less. That is why the force will decline when you go for higher draft. If we try to understand this declining nature of the force when you increase draft, we can look at this particular simple geometrical model of drafting, and then we can understand it very clearly. So, we will discuss this. This is a very simple model. This picture you have already seen earlier, is going to be repeat of the same picture. So, there is nothing new for you. So, what we see here is that, as told you earlier, the two vertical lines C C dash and E E dash representing the two nips, that is back pair of roller nip and front pair of roller nip. All the fibers are of same length, let us say their length is capital L, but the distance between these two nip is more than capital L. So, that means nip to distance a little more than the length of the fiber. Otherwise, all the fibers are of same length, they are straight and parallel with respect to the sliver axis, and line BC in this case, if you look at the line BC and line EF, just focus on these two, represent the number of fibers held by back and front roller nips. So, BC and EF. The line BQ is line going from B to the point Q, and the line PF, these two lines characterize the change in number of fibers moving at back and front roller speeds within the drafting zone. You have already seen such kind of lines in some other lecture. So, you are familiar with it. The triangle BCQ and EPF known as back and front beard and represents the surface area of the two group of fibers. So, the fibers which are held in the back nip, their number is represented by the line BC, which is let us say M1, and the number of fibers held by the front roller nip is represented by the line EF, which is M2, which is M1 by Z, where Z is the draft. And just the diagrams are shown here. These two lines BQ and PF are coinciding or crossing each other at the point R. Okay. Now, from here we go to the next slide. Let YB is the number of fibers in the cross section of the back beard. We call it back beard and front beard. Back beard means the fibers held by the back pair of rollers, and front beard is the fibers held by the front pair of rollers. So, YB the number of fibers in the cross section of the back beard at any cross section, and YF is the number of fibers in the cross section of the front beard, and Z is the draft. X is any location or any position in front of back rollers. So, let us say we have shown the position here x as if x is the point O on the draft field. So, this is at a distance, O is at a distance x from the back nip, that is from the line CC dash. E is a dimensionless quantity that can take any value from between 0 to 1. It represents the degree of disconnection between the front and the back beard. Basically, it represents the setting in terms of fraction of fiber length. So, therefore, the distance between the two nips is L plus LE. We take L common, it becomes L into 1 plus E. So, L is the fiber length and EL is the setting distance between them, where E takes a value between 0 to 1. Now, from here we can write that at any distance x, the number of fibers in the cross section is represented by the equation y b x is going to be m 1 minus x into m 1 by L. So, this is basically the equation of the straight line B q. If you look at the line B q and you try to find out what is the equation of this line. So, the equation of this line, because it has a slope which is negative, and therefore, the slope is basically in this case is going to be m 1 by L, and the negative sign indicates it is a negative slope. So, you all know the equation of straight lines which are y equal to m x plus c. C in this case is m 1, m is a slope which is negative in this case, and that is m 1 by L, and x is the distance from the origin. Hence, we get it m 1 minus x into m 1 by L, we take m 1 common and we get this equation, very simple. We follow the same procedure for YF also. So, how many fibers are there in the cross section which are held by the front roller nip, that is at the same location x. So, YFX, if we write, it is going to be m 1 by ZL within bracket x minus EL. It is also actually the equation of the line PF. If you follow the same procedure and try to find out the equation of the line PF is a straight line, you will get this particular equation. You try on your own, very simple, and if I from this, if we write m 1 by z, then we can write it is x by L minus E. So, these are the number of fibers in the cross section at a location x, fibers moving at back roller speed or fibers held by the back rollers at a location which is x from the back nib. The same is true for the other group of fibers also. Now, if I know these two number of fibers, now drafting force would be proportional to the number of contact points between the two beards, that is two group of fibers, and hence it will be proportional to the sum of the areas of the triangle OPR and ORQ. So, let us look at these two triangles, and so that to make the observation easy, we have written this letters O, P, R and Q in red color. So, it can easily catch your eyes, and if you see that the triangle OPR and ORQ, the sum of the areas of this triangle is actually representing the contacts points between the two group of fibers or contact area between two group of fibers. So, this is a geometrical representation of contact between the two group of fibers, because if this area is more, means more contact, more force. If the area is less, it means less contact and less force. That is as simple. So, at the point O, what will happen? Y f x and it will be equal to y b x, because the number of fibers either moving at back roller or front roller are going to be same in this at the point O, because both are equal to O r, and therefore, y f x will be y b x, and hence we can write from the equation that m 1 by z x by L minus E is going to be m 1 into 1 minus x by L, and from there we can cancel m 1 and we can get this equation, and from there if we simplify we can find out what is the value of x. So, we will know x in terms of parameter fiber length L, draft Z and E, which indicates setting between the two rollers. So, you can find out the value of x where the numbers are going, numbers of fiber moving at back and front roller speed are going to be same. So, after knowing x, which is basically O r, substituting the value of x at the point O in the above equation, that is the equation that represents the number of fibers in the cross section under front beard. In the same equation, if we put the value of x, which will give me the height O r, we will be able to find out what is O r. So, we will know what is O r, and O r is going to be m 1, it is just substitution of the value and simplification, we get this value m 1 into 1 minus E by z plus 1. Now, we need to find out the area of the triangle P Q R. So, if we want to find out the area, this is basically half base into altitude. So, we try to find out the area following this principle, half base into altitude. So, this is the half base and this part is the altitude. So, we multiply these two and we do the simplification part, we get the figure half m 1 L 1 minus E whole square by z plus 1. That represents the area of the triangle P Q R, and therefore, it represents the contact area between the two group of fibers, and hence force that is drafting force F is going to be proportional to this value. So, force is proportional to the area of the triangle and hence proportional to m1, L, E and Z. These parameters are important. So, there are 4 parameters which can influence drafting force as we see from these equations. These are m1, L, E and Z. Therefore, we can now write factors that affects drafting force. One is the fiber length L, the other one is the draft value Z, roller setting represented by E and number of fibers in the cross section of feed sliver. All of them, as we see in the previous slide, are going to affect, and you know, if you know the location of these parameters, whether they are in the numerator denominator, you can understand now how these 5 parameters are going to affect F. If we increase M1, that if I feed a thicker and thicker sliver, M1 is going to increase and therefore, drafting force is going to increase provided M2 remains same. L, if we go for longer fibers, again there will be more force that is we required, the drafting force will increase. If we increase Z, drafting force is going to go down, as we have seen earlier. That is, this equation takes care of the fact that is the part beyond the peak. After the peak value of drafting force, as you have seen, that the drafting force keeps on declining with increase in draft, and this particular equation in a way represents that. The other factors which can affect drafting force, they are the structure of the sliver, which is not coming into the equation, but we must know the degree of entanglement between fibers as it creates physical hindrance to slippage. So, entanglement that is there between the fibers will also influence the drafting force. More entanglement means more force. Therefore, we need more force while we try to draft cut sliver. If we want to draft the drawn sliver, that means it has been passed through draw frame once, fibers are a bit parallel to each other, we have removed the hooks entanglement, then we need less force. Similarly, if we think of drafting the comb sliver, we need less force because entanglements are not there, fibers have become straight and parallel, hooks are no more there. Therefore, with improvement in the parallelization or removal of entanglement, force is going to decline. Compactness, compact sliver will increase the degree of contact between the fibers and hence it will increase drafting force. Fiber characteristics, static frictional coefficient between fibers. So, what is the coefficient of friction between fibers? That also matters. So, with natural fibers we have no control on friction because they are nature's product, but if we want to, when we process synthetic fibers or when we process suppose dyed fibers or bleached fibers, then the natural wax is no more there on the cotton fiber. For synthetic fibers we apply spin finish and frictional coefficient gets affected by this, by the application of spin finish or lubricating oil, and there the more frictional coefficient is there, more is going to be the drafting force. Other thing is fiber surface roughness. Roughness of the surface also matters. Some fibers are rough. As an example, we can say wool fiber. Wool fiber have lot of scales on its surface. So, surface is not smooth, and hence while processing wool fibers, especially on drafting, what we do? We give lot of lubricating oil on the wool, so that the drafting force that develops can be minimized. crimp is also another factor. Crimp leads to mechanical interlocking between fibers, therefore, it can increase the drafting force if the fibers are crimpy in nature, but at the same time you have to remember the crimp will also decrease or increase the porosity of this fiber, because crimps mean they will not allow fibers to come very close to each other. So, the influence of crimp may be an increase in drafting force if the interlocking part or interlocking effect is too much. It can also decrease the force, because it will not allow the fibers to come close to each other, it will make this fiber very porous. So, both the factors will have its own influence. Another process parameter is draft zone setting in relation to the fiber length. If the setting is made closer and closer to the fiber length, then what is going to happen? The contact area is going to be more and more. In terms of that geometrical figure, the area of the triangle is going to be more and more if we decrease the setting, and hence drafting force is going to increase. Drafting speed is also another factor which can affect, because when the fibers have started movement, what matters is now the dynamic coefficient of friction. So, you should know that there are two types of friction coefficient, static and dynamic. And when the drafting process is on, static friction no more matters, what matters is dynamic friction, and dynamic friction is a function of speed. With increase in speed, dynamic friction coefficient increases, and therefore, drafting speed if we increase, we may get a rise in drafting force when rest of the parameters are same. It is because the dynamic coefficient of friction increases with speed. Okay. So, that is all about drafting force. Now, we will discuss another interesting topic, that is roller slip. Slip of the drafting rollers. In the modern draw frame, the slippage problem is no more there, that also you should know. This modern draw frames, the slippage problem is not there. It was there earlier with the very conventional and traditional draw frames. Even though it is not there, still we must understand why slippage used to be there, and therefore, what has been done to get rid of this problem. So, we have shown in this diagram where there are 3 pair of rollers, and you see the 3 rollers. The middle top roller earlier used to slip, it was prone to slip. So, we must know why it used to slip. So, let us analyze this. The backward slip basically would mean the sliver is pulled back by the rollers behind, causing top roller to run slower than the bottom roller, and therefore, it is a kind of slippage. That is, drafting is not happening, the sliver which is there behind this particular roller is trying to pull back the top roller. So, you should remember the bottom roller never slips, because bottom roller gets its drive directly from the motor through gears, and therefore, there is no scope for the bottom rollers to slip. It is the top rollers which can only slip, because they are negatively driven, that is they are friction driven from, because of their contact with the bottom rollers, but in between the rollers there exists fiber. So, the motion transmission is from bottom roller to the fiber and from fiber to the top roller. Okay. Now, here let us look at this diagram and focus on the material which is gripped in between the middle pair of rollers. Let us say T1 is the drafting force in the front zone acting forward, and T2 is the drafting force in the back zone acting backward. So, these drafting forces are acting on the sliver. The sliver part which is there in between front and middle, in that part the force T1 is acting, and the sliver which is there in between middle and back, T2 is acting on that sliver part. Other than the drafting tension which is there on the sliver, there is a frictional force acting on the bottom roller acting forward. See, the bottom roller is driving the sliver. Therefore, the frictional force between the middle bottom roller and the sliver is acting forward, and we have shown this in the other diagram, where we have shown the sliver by this orange color material, and the direction of forces also shown here. So, that the picture is much more clear here. So, F1 is acting between the bottom roller surface and the sliver which is in contact with the bottom roller, and because the motion is getting transmitted from roller to the sliver, therefore, frictional force F1 is acting in the forward direction. The another force F2, what I am showing here, the F2 is a reaction of the frictional force on the top roller. The top roller is receiving its motion from the sliver, that is from this band of fiber which is in between these two rollers. So, that force which is driving the roller is acting tangentially. The reaction of that force which is acting backward is acting on the sliver, that is the force which is F2. So, the force which are acting on the band of material which is gripped between these two rollers, middle rollers, there T1, F1 and T2, F2. Okay. Now, the slip condition and no slip condition. Slip condition is that T2 plus F2, if it is greater than T1 plus F1, in that case it is going to slip, that the slip is going to be backward slip. That is, the force on the sliver from behind is much more than the force which is acting on the same sliver from the front direction. So, this piece of sliver is actually receiving forces from the front side and from the back side. The total force acting in the forward direction is T1 F1, total force acting on the same material in the backward direction is T2 F2. If T2 F2 overcomes T1 F1, in that case the sliver is moved at the speed of back pair of rollers, and hence the top roller will start turning at a lesser speed and we will call it backward slip. This is phenomena of backward slip. The same inequality we can write T2 minus T1 is greater than F1 minus F2, or T2 minus T1 is greater than P, where P, which is the difference between F1 and F2, is called gripping power or gripping force. So, if the gripping power is less than T2 minus T1, then there is going to be a backward slip. So, the no slip condition will be just opposite to it, that is T2 plus F2 should be less than T1 plus F1, and this inequality, if we write it again in the next line, F1 minus F2, which we call P, that is gripping force, should be greater than T2 minus T1. So, gripping power, if it overcomes the difference between T2 minus T1, then there is not going to be any slip. The motion will be transmitted from bottom to the top, and the roller will move, that is V2t and V2b, these two speeds will be then same and there is not going to be any slip. So, this is what is important to avoid backward slip, that is P, which is the difference between F1 and F2, has to be more than T2 minus T1. So, we will see that practically what we should do to achieve this. We have to increase F1, because P is the difference between F1 and F2. So, how to increase F1 and how to reduce F2? That is what, then only P can be increased. We can increase F is F1 by having flutes on bottom roller surface. So, we want to make the bottom roller surface more and more rough, and hence flutes needs to be designed. That is why the bottom roller surfaces are not smooth, there are flutes or grooves on its surface, and there are many types of groove design. Idea is, by having grooves we are trying to increase friction between the fiber and the bottom roller. The other thing is, we can increase the top roller pressure. Ultimately friction is always mu into n. So, n can be increased by increasing the force on top roller. So, force on top roller has been increased, but here we have to remember that too much of force is going to bend the rollers also. The roller has to rotate against this vertical force that we apply on them. There is a lot of bearing pressure, and therefore, we need lot of energy to turn the rollers also. So, at the same time, when the force is acting continuously on the rollers also can bend. So, these are the difficulties also, but still we have to try to increase the top roller pressure, and that is what has been done, and we have to go for flutes on bottom rollers, where flute design also matters, that is the flute pitch, the depth, the land area, all this will matter. The other thing is, we decrease T2. How to reduce T2? Reduce draft in the middle zone and make it close to 1. So, we have seen that when the draft is, if the draft we are working which is less than the draft where we find the peak, generally a draft of 1.2, 1.4, 1.7, this is the range, is basically this draft is in the region 1 of the drafting force curve. So, here as you reduce draft, the force will decline, hence one can reduce the draft, have one common top roller on the two bottom rollers. This also makes the draft between second and third roller equal to 1. This is another way to, that is what we have seen, that in some drafting roller arrangements there is a common top roller, and thereby we make the draft between second and third roller equal to almost 1. That reduces the draft, and the other two drafting zones are separated by a neutral zone, and by having this we have been able to overcome the roller slip problem. The other thing is increase the setting in the middle zone, that could be another option. So, these options are there to settle the problem. From there we go to the next, that is forward slip. If the boycott slip is there is also a possibility of forward slip. So, in this case the sliver is pulled out from the back roller nip by the drafting force in the front drafting zone, causing top back roller to turn slower than the bottom roller. The sliver is pulled out from the back roller nip by the drafting force in the front drafting zone, causing the top back roller to run faster than the bottom roller. This is what is important, that, and the condition for this is the drafting force T1 acting in front zone is too excessive. Now, here we are showing the way the forces are acting on the piece of material gripped between the two rollers. Now, it is what we have seen earlier is basically the same thing, but instead of drawing two pair of rollers, I am showing you just one pair of roller, and you see the forces and their directions. T1 is acting forward as it was earlier, T2 F2 acting backward as it was earlier. F1 has changed its directions. This is what is different in this case. F1 has changed its direction. Why it has changed its direction? Once the slip starts, the material will move at a faster speed. It will move at the speed of the rollers which are in front of it, and therefore, the friction force on the material is going to act in the reverse directions. That is, even though the bottom roller is trying to move the piece of material gripped between them forward, but material itself is moving at a speed higher than V2B, that is this surface speed of the bottom roller, and therefore, the frictional force will act in the backward directions. So, when T1 is so large, drafting force is too excessive and the grip of top rollers on the fiber is not strong enough, this kind of situation is going to arise. And we can write, therefore, the slipping condition is when T1 is greater than T2 plus F2 plus F1. The T1 is so large that it is much more than F1 plus F2 plus T2, and this situation will lead to forward slip. Material will move at a speed greater than the speed of the bottom roller, top roller will move along with the material. So, both the top roller and the material will move at the speed of the rollers which are in front of it. That situation, if they arise, is going to be a forward slip situations, and the no slip situation also has been given here, that the inequality equation will just change, and that is how we get the no slip situations. So, if you want to avoid this kind of slippage, then increase F1 and F2, have flutes on bottom roller or increase top roller pressure. The other thing is decrease T1 and increase T2. So, how to decrease T1? Increase draft in back zone and reduce in the middle zone, or use two bottom rollers driving one common top roller, so as to make the draft equal to 1. The other thing is we can increase the setting. See, T1 becomes very large when the setting is low. If the setting is very close to the fiber length, the drafting force goes up. So, if I increase the setting, provided it does not generate too much of irregularity, then T1 can be decreased. So, playing with the setting, we can also play with the force, provided the setting does not create drafting irregularity, neither it breaks the fibers by stretching them, because they are too close to each other. So, we have to keep in mind both the facts. Within this, if there is a scope to play with the setting, we can do that. Other possibilities are already stated here. So, various means have been adopted by the machine manufacturers, and therefore, so many different types of roller arrangement we see, and with roller diameter variations also we have seen. So, there are many reasons why we have rollers of different diameters at the bottom and at the top. The way they are arranged is all because we want to avoid the roller slip, we want to ensure that the short fibers do not move in erratic manner. There is a guidance which can be given to them, and also to ensure that the total drafting zone actually takes very little space, because if the more I spread out the rollers, the more space is required. So, therefore, machine width is going to increase. So, we have to also see how to make a compact arrangement of the rollers within the given space. So, these are the many considerations which are there, and for designing the rollers and their arrangement. With this we close today's topic, and thank you.